Good afternoon, everyone. We start today our new year of seminars on Tuesdays, the Astrophysical seminars in Bologna. I'm a bit sorry there are not enough people as I expected, but okay, it's the first one after vacations. So our speaker today is Francois Rincon from IRAP in Toulouse. Francois got his PhD in turbulent solar convections and MHD in 2004 in Toulouse. He then moved for a postdoc at the Department of Applied Mathematics and Theoretical Physics in Cambridge, where he moved to accretion disks in MHD and hydro and nonlinear transition to shear flows. He became a CNRS research staff at IRAP in Toulouse since 2007. He's an expert in MHD and dynamo theories and plasma instabilities. And since last year, 2021, he's also the administrative head of IRAP High Energy Astro-Cosmic Extragalactic Group. And today he's going to tell us about the mysteries and challenges in nonlinear dynamos. So please, Francois, stage is yours.
Hello, thanks everybody for being here, and thanks to Franco for the nice invitation. So since this is supposed to be a short talk, I intended to speak about a few more things than I'm actually going to be able to do. So I skipped a few parts in the original talk I planned, and I decided to focus on the problem of small-scale dynamos, which is magnetic field amplification at scales smaller than the turbulent scale of a flow. I am currently working mostly actually on large-scale dynamos where you amplify magnetic field at scales larger than the scale of flows. But I'm not going to talk about this today, just to keep the talk short and consistent. So if you look at the problem of astrophysical fluid dynamics in general, there are many interesting problems that we can look at in this context, from the local solar neighborhood, solar physics, to planets, to the galaxy, to galaxy clusters, to accretion disks, stellar interiors, etc., etc. Astrophysical fluids are all around, and there are two salient astrophysical features that are very important in most cases. One is turbulence. Turbulence is an out of equilibrium processes which involves mixing and transport of variety of quantities. Can be angular momentum, can be chemical elements, can be linear momentum, etc., etc. Heat, you name it. And turbulence as an out of equilibrium processes is responsible for thermalization, dissipation, heating. And so it has an important effect on both transport and thermal regulation of astrophysical objects. So that's a bit everywhere in all these objects. And then another important feature, since most of the universe is made of hot stuff, most of it plasma, is that there is a coupling between this turbulence and magnetic fields. So most importantly in the talk that I'm going to give today, the question will be about the exchange between kinetic energy and magnetic energy. Namely, how can you generate magnetic energy out of fluid motions, turbulent fluid motion in a fluid, through something called the dynamo effect. So also when you couple things to magnetic fields, of course, that means you have an extra channel for heating the plasma through resistive ohmic dissipation. So these two processes put together, you can look at them from different perspectives, and the most used one and the easiest one is magnetohydrodynamics, fluid theory. So when we look at the kind of landscape we have for MHD in astrophysics, for magnetism and turbulence, so typically you have external steering at the system scale, which can be explosion, shocks, internal convection, tidal forces, accretion, lots of things that can happen. Then things cascade down through after being excited by instabilities that tap into the free energy of the system, typically gradients, thermal gradients, angular momentum gradients. etc., etc. So the dynamics associated with that is always multidimensional. So it ranges from almost 2 spatial dimension plus 1 time dimensions if you have a very rapidly rotating system, for instance, where things are kind of flattened, to 6 plus 1 dimensions if you go fully kinetic and you don't have collisions in your system. You need to use something called the Vlasov equation. And in that case, the description requires 3 dimensions of space and 3 dimensions of velocity space. In general, this dynamic is also highly nonlinear and multiscale. For instance, I put here some numbers for the sun, where the size of the radius of the sun is typically 700,000 kilometers. And if I take the typical scale for viscous dissipation, it's smaller than 1 centimeter. For the resistive dissipation, it's something like a few hundred meters. So that gives you very big scale separation between the two, and a whole range of nonlinear multiscale process take place between these injection scales and the dissipation scales. The other problem is that not all astroplasma are collisional, so you can get non-Maxwellian distribution functions. And in that case, fluid theory doesn't work. You need to go to the kinetic descriptions. And one good example of where this may be necessary is in the intracluster medium, where the typical scale of the system is up to 14 orders of magnitude larger than the smallest internal plasma scales of the plasma, like the ion Larmor radius, the gyration radius of ions around the magnetic field. So that's even more complicated in some sense. So if we also look even from a purely fluid point of view, I take a collisional plasma and I estimate what the resistivity eta is and the viscosity is in terms of temperature and density. And I take the ratio between the two. This is called the magnetic Prandtl number. So the nu over eta goes like force power of temperature divided by density, right? So if you are in a very hot and low density plasma, this number is going to be very large. This is what happens, for instance, in clusters and in the hot interstellar medium. On the other hand, if you go in denser plasmas like stars, stellar interiors, for instance, you end up in regimes which are at low magnetic Prandtl numbers. And planetary interiors are a bit special because they are in all sorts of weird states. Some of them are liquid metals, and usually they have very low magnetic Prandtl numbers. So I summarize this in this plot, where on the vertical you have something called the magnetic Reynolds number, which is essentially the ratio between the rate of stretching of a magnetic field and the rate of its resistive dissipation. And on the x-axis, the typical kinetic Reynolds numbers that everybody of you know, the ratio between the advection rate and the viscous dissipation rate. So in this kind of reduced parameter space that is typical of MHD, PM equal 1, the PM equal 1 line is around here. Simulations and experiments are in this zone, this black zone here. Clusters and galaxies are very high up. Here I've taken to put some broken lines. And planetary interiors and stars and liquid metal experiments are in this lower right zone. And accretion disks are a bit everywhere because the conditions in disks depend on how whether you are at the surface irradiated or inside in the midplane of the disk, where things are much less ionized. So you can get all sorts kind of parameters. In any case, what's important here is that you see that all these astrophysical systems, they have very high values of this Reynolds number and magnetic Reynolds numbers, even if you just stay with fluid estimates. And so that means if you want to understand what's going on in this system with the turbulence magnetic field, we need to look for asymptotic states where these parameters are to be very high. But you can't do that with simulations because you have finite resolution. And the second thing is we see all these systems with our magnetic fields in a nonlinear state where all the magnetic field is usually in dynamical equilibrium with kinetic energy. And so everything is nonlinear. You are not in a stage where things are growing linearly or whatever. So we also need to understand that. Right. So some key open questions on this problem of generating magnetic fields and sustaining them in all these different environments. So the general problem is how are small scales and large scale astrophysical fields amplified and saturated? By small scale, as I said early in the talk, I mean at scales smaller than the turbulence steering scale. And large scale means at scales larger than the turbulence steering scale. So for instance, in the sun, that would be the scale of the star itself. And also, one of the very complicated questions with this problem mathematically are the interactions and the competition between large and small scale effects, because everything can be hardly understood if you don't mix the two together in a nice way. Small and large PM-MHD dynamos on themselves, if you look at the two different extreme regimes I've mentioned before, they are two distinct problems. Each of them comes with its own questions. We don't understand how dynamos work at low magnetic Prandtl numbers and how they saturate in some way. We have a better understanding of how dynamos can grow at large magnetic Prandtl numbers, but we don't really know how they saturate either from the theoretical point of view. And also another problem that adds up to that, which I will briefly mention, is the role of emerging reconnection when you go to large magnetic Reynolds number, with the possible exception of some systems like the Earth's interior. Then on top of that, all of these are fluid questions, but then if I look at collisionless plasmas, like the ICM or hot accretion flows, this kind of stuff, well, you will have interactions between fluid scale and kinetic scale process. That means fluid scale instabilities, like the dynamo effect itself, or the magnetorotational instability, or whatever thing that's driving your system at large scale, and kinetic scale processes, which are like internal plasma instabilities, can be on waves, like Whistler waves, mirror and fire hose instabilities, etc., Weibel instabilities, you name it. There are so many of them. And this goes down to electron scale, which are even tinier than ion scales. And then in that context, of course, I'm not going to talk about that today, but there are connections between amplification of magnetic fields through a dynamo effect and the seeding of small field in the first place through some kind of plasma instability. And that's another whole problem in itself. Yeah, so the main difference between small and large magnetic Prandtl number, if you take a spectrum of turbulence in the two situations, so this is like the power as a function of the scale you are looking at. So you inject energy at the large force field scale, things cascade down in some way, which may be Kolmogorov or may not be Kolmogorov. Doesn't matter that much here. At low magnetic Prandtl number, like in stars, the resistive scale will be smaller than the viscous scale, and so all the magnetic energy, which is in blue here, the magnetic spectrum, will be within the inertial range of the turbulence. And so that means the magnetic field sees a very rough velocity field. On the other hand, if you go to large magnetic Prandtl numbers, the viscous cutoff is at scales much larger than the resistive cutoff. And in that case, you end up with a magnetic field that has some typical scales, not all of them, but some typical scales that are much smaller than the viscous scale of the flow. And that makes for very different types of dynamical phenomena. So for instance, small-scale MHD dynamos at large PM, these are from old simulation by my colleague Alex Chikoshin in Oxford now. So this is, for instance, a snapshot of the velocity field, which is very smooth here in this simulation, which have basically Reynolds number equal 1, so very laminar flow, but large magnetic Reynolds number, and you see that the magnetic field itself orders itself on a scale comparable to the scale of the flow along itself, but then it has reversal perpendicular to itself on a scale that is much smaller, which is a resistive scale. So the magnetic field orientation changes from one side to the other here. And so you have these very small scale reversals that you don't have in the velocity field. So in practice, that means you have a folded field structures. And that's typical of what you find also in turbulent scalar mixing in turbulent mixing problems, right? Essentially, the mathematical structure of the problem is almost the same. So you end up with this very folded field, which have a localized curvature and a very complicated geometry. At low magnetic Prandtl numbers, it's a bit different. when you go from large to low PM, you see a much more shredded magnetic field because, as I said before, the magnetic field lives in the inertial range of the turbulence, and so it gets shredded by all the inertial cascade in some sense. And also, it's harder to excite because of that, because there is much more structure in the magnetic field here. It's much harder to excite in simulation, and it took until like 10-15 years ago just to be able to even start to make it happen. Right. So that's for just the kinematic part. When you ask how you grow the magnetic field at large magnetic PEM, there is a mechanism known as the Zeldovich mechanism to explain how this all works in relation to also scalar mixing. And everything is well. At low PM, we can excite these fields now, but it's kind of harder to still hard to make a theory of how this works. When you go nonlinear, when the magnetic field starts to grow to sufficiently high level, you end up with nonlinear saturation, and that is even more complicated to understand. So I have no time just to go into a lot of detail about that. There is a lot of phenomenology. Essentially, what happened is that after an initial exponential growth phase of the magnetic field, when you start to randomly stretch it, the field gets into a regime where it first saturates with viscous scale flows, which is the fastest, corresponds to fastest steering scales that are most efficient at increasing the magnetic field. So you reach the so-called bachelor level here, where the magnetic field is still way below equipartition if the Reynolds number is large. And then from there, it's a bit unknown because there are many limitations in the simulation, but typically what is believed by different types of people is that there is an intermediate secular phase where the magnetic field, instead of growing exponentially, grows linearly, and then ultimately saturates in a regime which is in kind of global equipartition. But the asymptotic nonlinear state, if you all of this phenomenology is obtained usually when the Reynolds number, the kinetic one, is not too large and RM is larger, but there is no current understanding of the asymptotic nonlinear state of all that at very large RM and RE, both being larger than 1, which is usually typical of most systems that are MHE in Astro. If you are interested in this kind of the regime that's currently accessible, I recommend this paper by Amit Seta, which kind of explored with at relatively large spectral resolution with a spectral code, all these dynamics at magnetic Prandtl number larger than 1. At magnetic Prandtl number smaller than 1, it's extremely hard. We have even fewer clues of what's going on. So that's for what kind of what people know phenomenologically. Now the question is, there is an extra question that's popped up in recent years, and in recent years I mean it's still a work in progress. Namely that when you go to very large RM, typically a few thousands, the saturated magnetic field in the folds that you saw at large magnetic Prandtl number, they start to turn unstable to the Turing instabilities. That means you form current sheets in the fold reversals. And then there is an extra instability that kicks in that wasn't visible in the simulation up to this kind of resolution that I showed here. That starts to kick in, and that's brand new. You need to go to very high resolution with a spectral code already to obtain that, typically 512 modes per forcing scale, which if you take a lower like finite volume codes or codes with lower accuracy would probably translate like 2000 cube resolution or something like that to barely start to access this regime where you see the formation of plasmoids. So all of this is very much, well, terra incognita. You should expect maybe some results soon from the Matt Kuhn's group in Princeton, because they've been working on this problem for quite a bit. One consequence of that, because it's been a bit studied in 2D and pushed in a variety of simulation in recent years, is that there is a bit of theory being done by Alex Shikoshin, which I encourage you to read in his recent JPP review, which is still not finally published, but I think it will be a matter of a few months. One thing is that you start to see that once reconnection kicks in, you have plasma jets being spit out of the current sheets. And what's that mean? That means you get energy injection from the magnetic field into the velocity field. So the reverse of the dynamo, if you want. That's what you see on this plot, for instance, by Brandenburg and Rumpel. At small scale, the red thing here means that you inject energy from the magnetic field into the velocity field through the slingshot effect of the magnetic tension, while at large scale you continue to have injection of magnetic energy from the kinetic energy. And what seems to happen as a result of that is that you have a strong flattening of the spectrum of the velocity field, which doesn't go like k to the -5/3 anymore, or even k to the 3/2 if you follow this debate about MHD turbulence, but more something like k to the 4/3. So these are like some recent results that kind of give a hint that there may be a new kind of spectral law regime when you go to sufficiently high RM in there. And here is an illustration of what's going on at very, very large RM, up to 1 million in 2D simulations of MHD turbulence, where you see this kind of self-replication of reconnection plasmoid forming a new internal current sheet at small scale, which themselves become unstable to plasmoids, which form new current sheets, etc., etc. So that's a whole new phenomenology which is barely starting to be explored when you go to large RM, which even 10 years ago nobody knew about. Right. So this was just something I wanted to say about briefly about
20,
where. Sorry.
20 minutes.
Yeah, so I just give me 5 more minutes. I'll give a bit of a perspective into the plasma problem, the collisionless plasma problem. So these were just to indicate recent trends on this problem. So if we now look at the collisionless problem, namely now you don't have an MHD fluid anymore, but you have a plasma in which the mean free path is comparable to the scale at which you stir the plasma, which is something that may happen, for instance, in the intracluster medium. You can try to play the same kind of games of making dynamo simulation, making the magnetic field grow from some kind of forced turbulent flow. So we played that game a few years ago with some Italian colleagues, Francesco Califano in Pisa and Francesco Valentini, and with a hybrid Vlasov-Maxwell code. What's going on in that case? You need to distinguish between two regimes, because once you start to go in a collisionless plasma, you have to distinguish if the plasma is magnetized or not magnetized. By magnetized, I mean that the Larmor radius of particles, the gyration radius, is smaller than the scale of the system or larger. So when you look at the unmagnetized system, we kind of showed that the dynamo still works, and that it essentially works in the same way as the large PM dynamo. So here you see the evolution of a magnetic mode, which shows fold reversals like in the large PM dynamo. Once you start to go magnetized, things become much more complicated because of something called conservation of magnetic invariance. So in a magnetized plasma, you conserve these quantities, the magnetic moment of particles. And so if you increase the magnetic field, at the same time, you increase the pressure of the plasma perpendicular to the magnetic fields. And the parallel pressure evolves in a different way, so that you develop some dynamics of pressure anisotropy, which are essentially a trade-off between how much you stretch your magnetic field, d log B over dt here, and how much you relax it through any kind of collisional process, whether there are real collisions or anomalous collisions due to some kind of effective small-scale instabilities taking place. So it's a very complex problem which involves all the internal physics of the plasma. I don't have much time to go into details, but essentially when you start to trigger pressure anisotropy through stretching of magnetic fields, you end up with two instabilities, mirror instability when you have a positive pressure anisotropy, perpendicular pressure larger than perpendicular pressure, than parallel pressure. And when this is the opposite, you have the fire hose instability. So that means in regions where you stretch the magnetic field, like in these folds, here you would be mirror unstable, and here in this corner, you would be fire hose unstable. And what's going on in here, these things happen at very, very small scale compared to the scale of the parallel scale of the folds themselves. All kinds of things can happen. This was studied in for these two instabilities in a shear flow by Matt Kuntz a few years ago. When you put that in a big dynamo simulation, still things start to be a bit messy. I'm going to skip that one. I'll just show you this animation where you start to you try to drive a flow that is going to stretch your magnetic field. The red color here is positive pressure anisotropy. The blue one is negative pressure anisotropy. And you start to see this kind of small scale instabilities developing on top of the large scale spaghetti, which are mirror instabilities with density fluctuation, which are imaged here. So these were some kind of very discovery simulations that we did a few years ago. Since then, Matt Kuntz and his student Denis Saint-Onge did much higher resolution simulation with a hybrid peak code, which show all this beautiful dynamo with all the fluid scale and internal plasma instability stuff growing on top of the large scale dynamo in its full glory. So there are many questions about these simulations that remain. I don't have time to talk about them today. What's important to understand is that we are not in asymptotic regimes for these simulations either, with respect to the title of my talk, because we can't make the scale separation between the stretching rate of the large scale of the turbulence and the cyclotron scale of the gyration motions sufficiently large. We cannot separate the two enough. So we are not in asymptotic regime to study how all the anomalous scattering of particles by all this small scale instability works properly. And that means because all the anomalous scattering of the instability changes the transport property of the plasma, namely its collisionality, its resistivity, etc., etc. We don't get the right dynamics for typically the Reynolds number, the magnetic Reynolds number of the plasma, which are themselves now dynamical quantities evolving with the strength of the magnetic field. So there is a whole conversation taking place now among plasma people as to how this works, whether this could imply self-acceleration of the dynamo in some intermediate stages. At least to start to settle this question, we need like probably 100 times more scale separation than we have now, which would imply by today's standard volumes of simulations of several hundred of million CPU hours, which are of course not yet doable. But that's another frontier I just wanted to touch on today to give you a flavor of what's going on here. So I'm going to stop here. Going to my conclusion, I would say that even in fluids, if we are at spectral resolution of up to 512 to 1024 cube, which are several thousand points in schemes with lower precision, we are still in transitional regime. We are not yet in the regime of fast magnetic reconnection. We can't make relative scale separation between the resistive and the viscous scale large enough to see what would happen asymptotically to the nonlinear saturation of the dynamos. And typically also global astrophysical dynamo simulations, which have to make other compromise with geometry, stratification, etc., are at even smaller RM and are not generally in this kind of asymptotic regime we would like them to be right now. As for the plasma dynamo, as I said, there is also not enough yet enough kinetic fluid scale separation between the gyration scales and the fluid scales to understand properly what's going on in the astrophysical orderings that are relevant to understanding high energy astrophysical plasmas. Another problem I haven't mentioned is electron physics, which requires another ordering between the mass, because of the mass ratio between ions and electrons, where the simulations here are just in a very crude state where people use 20 points per directions just to try to see something. There are very few papers right now because it's even more complicated than the hybrid ones. So of course the future with all this problem is numerical. The problem is that it's very expensive, as much as cosmological simulations typically. And since we need to be careful about how we expend energy these days, I think we need to choose our battles carefully on this problem. So we can't afford just to run completely loose with resolution and do 100 different simulations. And so on top of that, from the theoretical point of view, we need complementary, well-motivated, effective series closure models just to kind of be able to prescribe in a physical way the effect of the small scale that we cannot resolve in simulations on the large scales in a way that makes sense dynamically and provides a good transport theory for all the fluid scale phenomenon. And there's a lot of development on this problem, from subgrid scale models to Landau fluid closures, etc. So that's another things that you can follow. If you follow the archive, you will regularly find papers, theory papers, trying to put out some new statistical MHD closures. And I'll stop here. Thank you.
Thanks. So Francois, meanwhile, you dissolved into the background, so we cannot see. Okay, we cannot see you anymore. We only see this.
Really?
Yes, I don't know. Some feature in the artificial background. Anyway, we have a question already from Bonanno, please.
Hello, can you hear me?
Yeah.
Thank you, Francois, for your nice talk. It was really nice to listen to this nice discussion. And I have the following question. I'd like to know if you have evidence for alpha square dynamo, and if you think that it's possible to understand the saturation mechanism of the alpha square dynamo from your simulation.
Right. So this I wanted to talk about this today because that's been my most recent work. If you have followed a bit, so the question is about large-scale dynamos, not small-scale one. Namely, how you make large-scale magnetic field from helical turbulence. Yeah. So the question with alpha square dynamos is, as you know, is the problem that once you start to get into the nonlinear regime. You have the if you have like homogeneous helical turbulence, you start to have a resistive bottleneck for the dissipation of the small-scale magnetic helicity, which prevents, on the other hand, the growth of the large-scale helicity because the total helicity in the system is conserved. And so that's what people call the catastrophic quenching problem in the dynamo community. So for quite a long time, people thought that there was this problem of catastrophic quenching, namely the larger the magnetic Reynolds number gets, the slower the dynamo, and you have problem to reach saturation and make large-scale dynamos happen on dynamical timescale. So Fabio Del Sordo and Axel Brandenburg and others in Axel's group 10 years ago, kind of, and even before that, Eric Blackman tried to find some ways out of this problem by looking at how you can expel helicity from the system, so to purge the small-scale helicity so that the large-scale magnetic field could grow on more efficiently, and you can do that. So some of my recent results have looked at another possibility, namely that if you have a distribution of helicity within your system, with positive helicity in some place and negative helicity in another, then you can organize internal fluxes of helicity to try to circumvent that bottleneck and make the quenching problem go away. And this seems to work, at least in the kind of toy turbulence models that I've set up numerically, but you need to go to high resolution, typically, as I said, 512 cube per forcing scale with a spectral method, just to get into this regime where resistive effect becomes subdominant compared to turbulent fluxes of helicity. I'm looking forward to other people having a look at this problem in the future to see if that, especially with global dynamo simulations like in spherical geometry, to see if this can help to bypass this quenching problem.
So if this is your work, recent work, I can find that?
It's just published in Physical Review Fluids.
Okay, thanks, great. Thanks
in December, yeah.
Thank you very much.
Okay, thanks. Are there more questions? If so, please raise your hand. Okay, meanwhile, I can ask one. So, yeah. In the cluster community, a few years ago, it was proposed, I think it was mostly from Kunt's group, that in principle, just using the development of plasma instabilities, the one you showed towards the end of the talk, you have enough amplification to justify micro-Gauss level magnetic fields that are routinely observed through radio observations in galaxy clusters. Do you think this is still true? Or yes, that this might be the seeding of something else?
Wait, I'm not sure I understand. Is the question that can you do a plasma dynamo that amplifies things up to micro-Gauss scale, essentially?
basically, if you can explain away the entire magnetic field structure that we can infer from radio observations, so omega parsec scale with structure up to tens of kiloparsec, just using small scale instabilities, growing towards larger scale, even without, let's say, large scale mixing motions by mergers. So just as a purely plasma process.
Oh, I see what you mean. I'm not sure Matt claimed that at any stage, did he?
I think it was, I can remember talks about 10 years ago, even in a paper, in which all of that can be explained in principle, at least the profile, but the question was the scales, but at least the radio profile of the Coma cluster, if I'm not mistaken, originally was proposed that it might have been produced by small scale amplification, the amplification of small scale instability.
I don't think that, I don't see how that would work, but maybe I don't see the right reference here. I mean, I guess it's kind of inevitable since you have stirring in clusters and all that you will get large scale motions anyway, right? So in this respect, I would say that right now, what we understand about the parasitic effect of these instabilities and all the anomalous scatterings that they bring and how they change the transport properties of the plasma, that doesn't seem to compromise the ability of the large-scale stirring to amplify the magnetic fields. The question is more how it does it, because so if you read Matt and Denis' most recent paper in the Journal of in the Journal of Plasma Physics, they claim that there are different regimes where the plasma instability kind of saturate in different ways. So it's a bit of a subtle discussion. There may be regimes where things self-accelerate. There may be regimes where things look like isotropic MHD. There may be regimes where things look like anisotropic MHD. All of this, all our understanding of that, you can make twiddle algebra arguments with that. But we are very limited with what we can figure out with that, because we would need higher scale separation for the ratio between the fluid scale stuff and the internal plasma scale stuff. But in practice, none of these regimes, all of these regimes, you can still amplify the large scale magnetic field through a dynamo effect, just at slightly different rates. So, you know, I'm looking at this from a plasma physics perspective. There are lots of very rich and interesting plasma dynamical phenomena in here. But if you want a message about what this means for clusters, my answer would be that ultimately everything will be fine. It's just that the time scale on which this happens, how this happens, is, I think, are very nice problems to solve. But they are maybe not relevant at zeroth order to the large, what you see at large scales today in clusters. Yeah.
Okay, and still connected to that, you think there is hope to include in a sort of MHD picture we can attach to cosmological simulations effects from the kinetic regime and some sort of subgrid modeling? So
right. So the first things to do in that respect, and this is actually something I'm trying to take steps just by making not a cosmological model, but more like a local model. Maybe you and that's also the question of how you go with magnetothermal instability and all that. I encourage you to read that paper by Denis, because what they've done essentially is try to use Braginskii MHD, which is something you can do in any code, including cosmological code, but with a bit of coding, but that doesn't change fundamentally the nature of your code, right? It remains MHD, and try to see what happens if you go with different types of Braginskii MHD. One they've tried is regular anisotropic viscosity, right? So you get these kind of pictures for the dynamo in this case. And the other one is one where you use Braginskii MHD, but you also kind of limit the effect of the Braginskii velocity in a way that mimics the saturation of the kinetic instabilities. So you may call that a closure. And in that case, you see slightly different pictures for the structure of the magnetic fields. That come from your different, the way you really close the system and what that means for damping of the velocity fluctuation that amplifies the magnetic field, its stretching, etc. There is a whole very interesting discussion actually on things becoming anisotropic when you go kinetic, and where you need to, if you want to model that in MHD, you need to come up with like something like a parallel Reynolds number and a perpendicular one that are different. The parallel one will tell you the rate of stretching, and the perpendicular one will tell you the rate of perpendicular mixing. And the competition between the two, if you have high perpendicular mixing and small parallel stretching, makes the dynamo more difficult and more inefficient. So by modeling this kind of effect with limiters or without limiters using anisotropic MHD, Braginskii, you may be able, just with a fluid code, to look at more things about the structure of magnetic field in this kind of environment without having to go full kinetic.
Cool. Okay, I have a look.
So these are just local simulation in periodic cubes, right? But
sure.
There is no reason you can. People have already implemented in cosmological simulation, like Braginskii conduction for magnetothermal instability and HBI and all that, right? So it's just the same with the viscosity.
Okay. Okay, cool. Unless there are other hands raised. Okay. Okay, I think this is it for today. Thanks again for being our first guest of the year. And we reconvene again next week.
Right. Thank you very much. Sorry for being a bit fast. That was hard to just to fit into less than half an hour.
No.
Anyway, thank you.
It was perfect, I guess. Okay, let me stop the recording.